integrate the square and then integrate and add the triangle that you're integrating. No,
So do,
from like the, yeah.
so do that?
And
No,
then-
that's not what
no.
he's saying, no.
No, that wasn't what you're saying? Oh, well.
But you can go from here to here, integrate that, and then go here to here, integrate that, but I wouldn't double it because again, you don't necessarily know. Remember, this is on the ground, right? And we have a surface above it. And so that surface up on top may not be symmetric over here.
I think he's trying to say how we can do the integral. He's thinking of splitting it into more parts. But we don't need to do that because we can integrate with respect. We can.
Yeah, so what we need to do here is recognize this is a type 2 region. A type 2 region. Type 1, our x's are between two constants, our y's are between two functions of x, right? Like this. This is a type 1. Right? So this was like x and this was our y's. That was type 1. Type 2 was this basically sideways. We have the same exact thing here, but we're using u and v instead of x and y. So this is a type 2 region in terms of u and v.
Out of curiosity, if we had said v equals x plus y and u equals x minus y and the other way around, we would have had type 1, wouldn't we?
Then it would have turned this, so yes, it would have been type 1.
Okay, so basically, if we wanted to at this point.
But what's wrong with type 2? You don't like type 2?
No, there's
Oh,
nothing wrong with it.
okay.
They're
What
both
was your...
just as hard, or just as easy.
Yeah, they're equivalent. You just have to determine what the equations are. So I would, if I were sitting here, I'd be like, why go from a trapezoid to a trapezoid? What do you gain, right? Well, the gain is we can integrate that now. That's the gain. Like we'll be able to integrate e to the u over v. We can't integrate it like this though. All right, let's proceed. All right, let's proceed. We have our region of integration. This is S. And let me go ahead and let's determine what this is as a function, like, you know, our v's are between what two constants here in this region? 1 and 2. And our u's are trapped between two functions of v. So that means our u's are trapped between that one and that one. So we need to write these. Like, yeah, but we can't use x and y, right? So what would this be? Like, you know, what would this be? That line, what would that line be if it was x and y? It would have a slope of 1, and it would have y-intercept of 0. So that would be y equals x, right? So this is really v equals u, right? And this one over here would be y equals negative x. So for us, it's really v equals negative u, right? But now we need to solve each of these equations for what?
U.
For u. Just like if it were in terms of like y equals x, we would solve it for x if it's type 2. Here, same thing. I know it's, look, I'm the messenger, okay? I'm the messenger. So what are our restrictions on u? U is between what? Negative v and v, okay. So we have our limits of integration, right, for our double integral. I think we're ready to set it up. Oh, wait, hold on, we forgot something. The Jacobian. We still need the Jacobian. So let's get our Jacobian. So the Jacobian, right, we need to take the determinant of this. We need the determinant of this. So we got to take partial of x with respect to u and all that stuff. And that, we're going to use these, right? These right here. So what is the top left corner of that going to be? Partial of x with respect to u. 1/2. This is about to answer your question about angles and stuff. I think this is going to tell us a scaling factor. If it's 1, everything came over identical to what it was, just got turned. Okay? So let's see here. What's next? Partial of x with respect to v. X with respect to v. 1/2 again, right? Okay, partial of y with respect to u. Half again. Partial of y with respect to v, negative 1/2. So now do your little diagonal thing. So you get negative 1/4, and this is going to be absolute value when we're done. And then minus 1/4 again. So that's going to be minus 2/4. So minus 1/2. Absolute value, 1/2. So it looks like everything got scaled down by 1/2, factor of 1/2.
Have it scaled up by a factor 2, because if we're multiplying s by 1/2, then
Wait, say again, or what?
when we went from d to s, d was scaled by a factor of 2, right? Because we're scaling s by a factor of 1/2 to get what our
It was scaled by 2, yes.
okay.
All right, double integral, I think we can set it up. I think we're here. Let's try it. I'm going to leave that right there. So we have now the double integral, right? Now, what limits, well, we can do the inside. What does the inside become? E to the u over v, right? That's what we were shooting for. And then Jacobian, 1/2, pull it out. And then our order of integration here is no longer up to us. So we're going to go what? du first, then dv, because v has the constants on it. So we're going to go 1 to 2 here, and then negative v to v there. I say we take this one. I say we take it all the way. We've suffered enough. We can just suffer a little bit more. So this is 1/2 integral 1 to 2. And then now the antiderivative of e to the u over v with respect to u. So if you're having trouble with that, look at that like we're trying to find the antiderivative of u over 4, let's say. That's the same as e to the 1/4 u. So what would the antiderivative of that be?
It would be, you probably would use
4e to the
4e, this would be, the antiderivative of this would be 4e to the 1/4 u. Because if you take the derivative of this, derivative of that is itself, right? But then derivative of that would be 1/4, right? So you'd have to kill that 1/4 by putting a 4 out here, right? So for us, this is really like e to the 1 over v times u. So the 1 over v is like the 1/4 was. So what's the antiderivative going to be? V e to the u over v, right? And where are we evaluating that? From what? From u equals negative v to u equals positive v. Are y'all still there? Okay. I remember as a student when we got to change of variables, I remember just feeling very uncomfortable with it. It's just a weird thing. There's a lot going on here. 1/2 integral 1 to 2. All right, let's go ahead and plug some stuff in. So what happens when u is v? Well, that's actually pretty nice, right? That's just going to become 1, and e to the 1 is just e. So that becomes e times v, ev. And then minus, now let's plug in negative v. Negative v goes in there, you get negative 1. So e to the negative 1 is just e to the negative 1, or 1 over e, right? So we're going to have minus e to the negative 1 times v. Yeah. Got it? dv. Integrating that with respect to v now. So this becomes 1/2. The antiderivative of this is what? E to the v squared over 2, or 1/2 ev squared, however you want to do it. 1/2 ev squared, and then minus, same thing, right? 1/2 e to the -1 v squared. And we're evaluating that from v equals 1 to v equals 2. Which is 1/2, kind of running out of room here. See if I can squeeze that in there. So the 1/2 on the very outside of everything. Now let's plug 2 in for v. 2 is 4. Half of that, 2. So 2e minus 4 again. Half of that, 2 minus 2e to the -1. And then plug in 1 into those. So 1/2 e, right? That's there. And then minus 1/2 e to the -1, which is 1/2, damn it, I'm taking it all the way, 2e minus 2e to the -1 minus 1/2 e plus 1/2 e to the -1. Combine like terms. This one and this one. 3/2 e. 5/2, yeah. What is it? It's 4/2 minus 1/2, so 3/2. So we have 1/2, 3/2 e, and then what about these two together? Minus 3/2 e to the -1. I'm going to pull the 3/2 out. 3/4. That's the exact answer. I finally wrote e to the -1 is just 1 over e. Okay, I'm curious to see what the computer gets. I'm going to leave everything in terms of x. The computer can do it. The computer can definitely get this answer. It can get an antiderivative, but it was really complicated, wasn't it? But if I give it a definite integral, it can do it numerically. So let's just start this bad boy over again. Y'all ready to see this? Let's see what happens. Do y'all feel good about that answer?
Yeah.
I'm about 60-40 on it right now. All right. This is going to be a little complicated because I have to figure out my parallelogram real quick. Yeah, it was 2 integrals, so hold on. It was, y'all help me out here. This point was 1, 0? 2, 0, is that right? And then this, so this was 0, -1. And then this one was 0, -2. Okay, so y'all understand what I'm going to do right now? I'm about to break this thing up into 2 separate integrals. I'm going to do it over this one. I'll call it D1 and then D2 here. On D1, what's that line right there? Y equals x minus 1. This one is y equals x minus 2. So when I do my double integral over D2, I'm doing this very quickly here. I'm going to go from 0 to 1, 0 to 1, and then between these two. X minus 2, x minus 1, and then be doing e to the x, what was it? Plus y on top, or minus y? Plus y on top, x minus y on the bottom. dy dx, I'm going to do that. And then when I do it on D2, what's the integral for D2? So I go from 1 to 2. And then what's the bottom function? X minus 2. And what's the top function? 0, and then I'm going to integrate the same thing. I'm going to do both of those integrals on the computer and see what I get. While I'm doing that, would someone mind typing this into their calculator and getting us a decimal answer? So I'm not quite sure it's going to give us a numerical answer. I don't think it's going to give us the exact answer. I'll actually be pretty surprised if it does. So x minus 2, x minus 1, we're integrating exponential of x plus y over x minus y dy dx. I'm just curious to see what it does right here. Oh, I didn't close it. See, it told me that though. Oh, it's thinking. Uh-oh. Oh! Okay, so what I need to do is put in a decimal, and it'll give me a numerical. I feel good that it will. Whoa. Okay, there we go. All right, so now what I want to do is just take that same thing. Let's just copy that. And let's paste it here. And now we're going to go from 1 to 2, right? And then here we're going from x minus 2 to 0, right? There. Oh. Did anyone do it yet?
About 1.7.
Yes. That's what we got here too. All right. That's what you got?
Yes, sir.
Okay. So the computer could do that integration numerically, which means it's going to run a power series and go out to a certain decimal place and then be able to kick back a numerical answer for each stage of the integration. Does that make sense? It's doing that. And then get a numerical approximation. We, humans, had to transform the variables first, and then we could do it by hand. That's good. I wasn't really 60-40. I was like 85-15. All right. That's pretty much it. You have a homework assignment with that. See how it goes. We got 20 minutes. I'm going to look at our schedule real quick. I think we're a day behind. More than a day? Uh-oh. Today's the 8th. Change of variables? No, we're right on schedule. Perfect. Good. There's one more thing in this section I'd like to show you, but I will not test you on. But that doesn't mean that I want you to just like totally tune me out. Unless you're ready to tune me out like, 45, 50 minutes ago. Back in spherical coordinates. Remember when we do spherical? Remember I said that when you do the conversion from Cartesian to spherical, you had to include this rho squared sine phi? Remember that? Well, I haven't talked about this yet. What we've been doing so far is we've been taking a region in two-dimensional space, transforming it into a new region in two-dimensional space. But a spherical, changing from Cartesian to spherical, is from three-dimensional space into three-dimensional space. So how does that change our formula? Because our formula right now looks like this, right? Yeah, so what we have to do is we have to add a new variable in here. We now have what? You're going to have triple, right? You have a triple integral over some E region, function of three variables, dv, sorry. So how would we get a triple integral change variables? Well, I'm going to write the formula down on the board. See if I can do it out of memory first. And then I'll double check the book. But you've got the triple integral over E of f of x, y, z dv. If you make a transformation, all right, your transformation takes x over to, x is some function of u, v, and this time w. So you have 3 variables now instead. Your y now becomes some function of u, v, and w. And then your z becomes some function of u, v, and w. Then this integral becomes the triple integral over, I don't want to say e, I'm not sure what the book uses. I'm not going to look at the book yet. We'll just call it e bar, okay? Just, it's not e, it's e bar. It's the transformation of e. Then it's going to be f, but you've got to change all of these x, y, z's into their transformations, right? So it's f of x of u, v, w, y of u, v, w, z of u, v, w. And then what comes next? The Jacobian, right? But you have 3 variables, right? You have 3 variables. So your Jacobian now looks like this. You have to do the determinant again, just like this. So this right here means to do this little diagonal, this, right, times and then across, subtract. You have to do it with 3 things now. So it's going to be the partial of u with respect to x, partial of u with respect to y, partial of u, oh shit, I've got that wrong, sorry. Pardon my language. I meant to put partial of x with respect to u, partial of x with respect to v, partial of x with respect to w. Then partial of y with respect to u, partial of y with respect to v, partial of z, Robert, with respect to w, and then last one, partial of z with respect to u, partial of z with respect to v, partial of z with respect to w. Okay, there we go. d v, whatever our new thing is. Yes, I'm sorry? So how do you do that? Right, so how do you do that? That's why I wanted to show this to you. Do you get the idea though? And what if this was a function of 4 variables, x, y, z, and t? Then it would be the same transformation, blah, 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 and then you need the Jacobian of a 4x4 matrix, basically. So let's take a moment, not too long, but let's take a moment to talk about how you do the determinant of a 3x3. Because this one I think everyone's comfortable with, right? So let's do an example. So that we're going to step away from this real quick. And let's just take, how do you do the determinant of A, B, C, D, E, F, G, H, let's go with I. Okay, I'll use I. That's not the imaginary unit, that's just the letter I. So how do we find the determinant of this? There's different ways. I've seen all sorts of different shortcuts on how to do this. I'll just pick one. So one way I've seen to do it is you just remember this is plus minus plus. Has anyone seen this way? Okay, so here's the way it starts. What you're going to do is start in the top left corner like this. And it's A, you're going to take positive of whatever that is, A, and you're going to write it down. It's going to be A times, now when I pick this A right here, that means I'm going to close off this column and I'm going to close off that row. Let me do it this way. Okay? Because that A is in that position, I close off the top row in the first column. And you see this E, F, H, I? I'm going to write that down. E, F, H, I. Okay? So I have to do the determinant of this and that, like that. And when I'm done with it, multiply it times A.
And it doesn't matter that that's negative and that was positive.
Nope. You'll still have to do this minus this. But this will be positive out here. Like, well, if that's -4, that's -4. But you don't change the sign. Okay? Now, the next one, what we do is we move to B. But this time I'm going to do minus. So I go minus B, and then times, now what do you think I use in here this time? DFGI. So I close off this and this, and what's left is DFGI. And you put that there. Make sense? DFGI. And then plus, because it's plus on the last one, C, close off this and this, D, E, G, H. Yeah? So what if there were 4 of these? Look at how disastrous this gets fast. Imagine that there were 4 of these. I don't want to go through it, but let's just look at it because it's fun. Okay, imagine if you had 4 of these, and I'm going to stop doing it that way. I'm going to do A1, A2, A3, A4, A5.
The Jacobian with 3 of them, and then you have to do this again.
Yes. 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 I need one more. 14. I don't really need all this here because I think you already see what's going to happen. So to do this, plus, minus, plus, minus. Start here, okay? So the first piece would be A1 times cover, cover. Now you have 3 by 3. That goes here. So that would be what? A6, A7, A8, and then so on and so forth, right? But then how do you do this?
And then you do A6 before.
But there will be like a bracket around all of that expanded out. And then your next piece would be minus A2, then another 3 by 3 that gets expanded. Do you see how that becomes extremely complicated? And you just keep doing this. You want to go 5, 5? No, we won't do that. All right, with that said, now you see what this is going to be. This is going, when we compute this, it'll be the partial of x with respect to u times that little determinant in there. And then we'll have to move on to the next one, next one, next one, right? Okay, here we go. We're going to do it. Let's go back to 12.7. Did I close it? I did. Let's go back to 12.7. And here are the spherical conversions that were given to us. All right, I'm going to write these down. Okay, I'm going to write these down. But to make it easier to work with, can I call this U instead of rho? Let's call this V and let's call this W, because those are just 3 like dummy variables, right? So what is our thing? We have x equals U cosine V sine W. Y is U sine V sine W. I'm going to be able to finish this. Z is U cosine what? W. Okay. So that's it, right? That's it? Now we're ready. Anytime we want to use spherical conversions, we must do whatever the spherical conversions are in our function. We must change our limits of integration however they change, but then we need to compute the Jacobian determinant. And we're going to do that right now. And this is going to be messy. So let's just focus on that part right there. So this right here, our Jacobian, and we'll do an absolute value at the very end, is going to be the partial of x with respect to u. What's the partial of x with respect to u? Oh, you know what? Yeah, let's just do it. What's the partial of x with respect to u? Yeah, hold on. I'm just wondering if, yeah. It's cosine v sine w. Okay, times, now what goes in here? So I'm going to be doing, let's just isolate this real quick. Partial of y with respect to v. What's partial of y with respect to v? Okay, right? And then let's do this one. Partial of y with respect to w. U sine v cosine w. You understand what I'm doing? Okay, and then this partial of z with respect to v. Sorry, hold on. Partial of z with respect to v. Yeah, there is nothing there, right? There's nothing there. 0. Partial of z with respect to w. Negative. u sine w. Okay. Why did I make that so big? I don't know why I made that so big. Okay, that part, right? Now what? Minus, we're moving on to this now, right? So minus, and we're going to be looking at these two pieces. And I'm out of room here. So minus partial of x with respect to v. Negative u sine v sine w times, now another determinant. And I'm doing partial of y with respect to u, sine v sine w. And then partial of y with respect to w, which is u sine v cosine w. And then this one, partial of z with respect to u, cosine w. And then partial of z with respect to w, negative u sine w. One more. Plus, where am I? We need this piece, right? And then we're going to be doing these four. So partial of x with respect to w, u cosine v cosine w, and then partial of y with respect to u, sine v sine w.
I'm just getting that from the top that we already got it.
Oh, we already did. What is it? U cosine v sine w. And then z with respect to u cosine w. And then 0. Right? We all agree? Still have 8 minutes. Okay, so this becomes, I'm going to do this all in a big line here. Cosine v sine w times, now let's do this determinant here. This times this, right? And then minus this times this. But we have a 0 in there, so that's going to kill that second part off, right? So it's just going to become negative. And can I put the negative out in front here? Because of multiplication. Negative, what? U squared cosine v sine squared w, right? That's our first one. Okay, minus, look, check this out. This is minus minus, which is going to be plus, right? Plus, I can't erase that. U sine v sine w, that's that part. And then here to here, so times sine, u, shoot, it's another minus, isn't it? Yeah, so I'm going to have to change that plus to minus again. Let's do this. Let's change it to minus. I'm trying to go fast here. I hope I don't make a mistake. So that's minus sine v, u sine v, sine squared w. But then what? Minus, so minus this. See, that's why, yeah, we can't pull that out. This has got to be minus, because that's being subtracted. Okay, so let's look. Let's leave this plus. Let's put a bracket here. Let's make that minus. Do y'all follow what I'm doing there? Because it's this, which is a plus, but then this part right here was negative. This part's also going to be negative. So minus u sine v cosine squared w. Dang it. Okay, I'll fix that in a second. And then we have this last one, which is plus u cosine v cosine w. And then this one is gone, right? The other one is minus u cosine v sine w cosine w. Okay, get rid of this now. Looking at this first one right here, let's pull that u squared out. So we get negative u squared, negative u squared. I have a cosine squared v, and I have a sine cubed w, don't I? Y'all agree that's that first one? Okay, on this one, I think that's not there. Let's go ahead and distribute this here and then here. Do I want to do that? No, check this out. Look right here. Look at this right here. In the brackets, I have u sine v sine squared w minus u sine, you see it, sine v cosine squared w? Do you see that in here? I can pull out the negative sine v. And what would I be left with if I pulled this and this out? Sine squared plus cosine squared of w, and that would be a 1, wouldn't it? So I'm actually not going to distribute this through to both. I'm going to just take this and multiply it times that, which would give me a minus, right? U squared sine squared v sine w. Sine squared v sine w. We're almost there, and I am, yeah, still got time. Okay, what's next? This one? Minus u squared again. Do we get anything nice? Cosine squared v. Cosine squared v. Cosine squared w. And then we got this weird sine w, right, just by itself? All right, can we do anything with this? Yep, right here. This guy and, oh, they're right next to each other. Okay, so I can just,
Take on an entire negative u squared.
yeah, those two right there factor out a negative u squared sine w, right? No.
You can factor out of all of them. They take out a sine w. So negative u.
Sine w out of all of them, okay. And a u squared and a negative. We can do that? That's what you were saying. Negative u squared sine w. It's a little easier when you're sitting back and I'm not, like right here, I'm trying to do this. Okay, this. Okay, so that, and what's left here? Cosine squared v sine squared w. And then plus, right, because we pulled a negative out, sine squared v plus cosine squared v. I was wondering when it was going to happen. Okay, there we go. Sine, whoa, what? Cosine squared, I thought, okay, cosine squared w. Is this going to happen? Yes, okay. Yes. Okay, so these two together now, this one and this one, they both have in them cosine squared v, right? So what happens if I pull a cosine squared v out of both of those? So I pull out the cosine squared v out of both of those, you're left with sine squared w plus cosine squared w, which is 1. So that's gone, right? And then you're left with plus sine squared v, but that's 1. And so you get negative this, right? But remember, it's absolute value. So what is the absolute value of this? U squared sine w. And what was u really? That was rho, right? And sine, what was w? It was phi. That's pretty awesome, huh? That's a lot of little Pythagorean identities in there, right? Lots of things that could have gone wrong with that calculation. I'm surprised I actually got it. Right? I usually don't go after that problem because there's too many places for error. But okay, so that's where your spherical conversion of rho sine rho squared sine phi. That's where it comes from, the Jacobian determinant. All right, well, I do not have a take-home exam for you. I'll probably have that next class, the next mini exam, number 5. That's it. We start chapter 13 next time. Last chapter of the book. Vector fields is where we start. I knew you were going to say that.